Hello everyone, this is another Ansys Fluent tutorial for multi-phase flow simulations, which is provided by the Ansys itself. And if I go to the problem description quickly, this is basically a printer ink injection system. So if you see this geometry here, you have this ink chamber at the top and you have the air chamber at the bottom. So this chamber is filled with ink, and at time 0 it starts to inject the ink to the air chamber, which is located here. So if you look at the geometry dimensions, like the height of the ink chamber is like 1.1 millimeter, and the height of air chamber is just 0.28 millimeters. So the dimensions are quite small, and I think we can now go to the Ansys Fluent and start simulating this problem. I will talk about the boundary conditions when I get into the problems later. So I'll go to setup. So since the dimensions are quite small, I'll go for double precision, and this is a 2D simulation as well. I press OK. I have my mesh already available on a folder on my desktop. So I click on File and then Import Mesh. The mesh is located on my desktop on this folder. So if you look at the geometry now, this is my ink chamber and this is my air chamber, and as you see I have only half of the geometry because this is an axis symmetric problem, and it is symmetric around this axis. So the first thing I would like to turn on is the axis symmetric option here, and this is of course a transient simulation. I press transient here as well. So if I go to the multi-phase flow model, I would like to use volume of fluid for this specific simulation, and I keep the default settings for volume of fluids, and I press OK. So regarding the viscous, this is a laminar problem, so the geometries are small, and the properties of fluid with respect to the velocity makes this problem laminar. So I'll go to materials. So basically I have one material as air as a default, but then I need the ink as well. So I go to Fluent database. So the ink is supposed to have the same properties as water liquid, and this is an assumption of course, but I will keep water liquid as my secondary phase. Click on water liquid and I just copy, and I close this down. So now if I go to setting up the physics and the phases and click on list show all, my primary phase would be definitely air, because most of the fluid domain is flow domain is filled with air. So my primary phase is air, and my secondary phase would be ink, and we know that it's actually water liquid, and I press OK and I close this down. But before doing this, maybe I would like to have the full geometry on my screen, so I would like to mirror this geometry with respect to this axis. So I will go to viewing, then I will go to views. So the front views, I would like to mirror it with respect to this axis, which is already defined, and I just press apply. So now you can see you have the full geometry available here. The next step I would like to take is the scales, I think, because as you see the scales, when the geometry is created in a space claim or whatever softwares you have, you can see that the domain extents are quite big, and it's not what we have in the in the problem descriptions. So I need to scale this down. What I need to do is specify a scaling factor of 1e minus 6 for both x and y, and I just scale it. So now you can see that the domain extents is according to the problem descriptions, and then I can close it. There is one other thing I would like to change, and that is the units here and the surface tension, that I will work with that later in this tutorial. I would like to have the units to dm over centimeter, and perhaps the length as well. I would like to have it on millimeter. So I will close this down. The next thing I would like to change is actually the boundary conditions. So the axis is axis, so you can see this is the axis. The default interior is just the interior, but then I have the inlet velocities at the inlet for the mixture, which is defined according to a user-defined function. So as I said, the velocity in the inlet is 0 at the beginning, at initial time, at t equal to 0, but it increases to 3.58 right after the simulation starts, and it decreases according to a cosine line for 10 milliseconds, and then after 10 milliseconds the velocity at the inlet reaches back to 0. So what I need to do is to load my user-defined function that I have already defined, and if you want to take a look at that, I need to find my, here is the inlet one. So if I just take a quick look at my user-defined function, there are some things that are included in the beginning, like UDF, SG multiphase, and flow, and then it comes to the definition of membrane speed and threads and variable numbers, and then you're getting the time from this one as well, and then you start a loop here, and you put a if function here. You say that if f time is less than 10 micro per second, then the inlet velocity will be defined as 3.58 multiplied by cosine pi f divided by 30 e minus 6, or else the f profile would be 0. So that is the definition we were thinking about for the inlet velocity. So what I need to do is to load this one as well, this user-defined function, and interpret it. So I go to user-defined f functions and interpreted it, and I need to go to source file name. It is located on my desktop. Tutorials, this one I guess, and then just interpret it. Now you have this f function available for your inlet velocities. So you double click on inlet velocities, and instead of constant velocity magnitude, you go for this UDF functions that you defined here, and you press OK. Since at the inlet you only have ink, you double click on ink and put the volume fraction to 1, and you press OK. The outlet is actually at constant pressure of 0, gauge pressure 0. You don't change it, but you would like to have this backflow volume fraction of oil set to 0. You don't want to have any oil coming back from this boundary condition here, because this is just air outside, there is no oil. And I press this one to OK as well. I forgot one thing before jumping to this wall conditions, and that is the interaction between the faces. So I'll go back to setting up the domains, or setting up the physics, and then to the faces and the interactions, which is also important. So there is a surface tension actually between the ink and air at constant value of I need to take a look at my notes. The surface tension is 73.5 Dn per centimeter, and I would like to turn on this wall adhesion as well, the wettability properties. I will come back to that as well in the boundary conditions. For the moment I will turn this on, and if you turn this on, then the walls that you have defined, for example, if you double click on them, you will see there is contact angles that you can define for the wall adhesions. Let's take a look at the walls definitions here. So I will go to display. So as you see, there are two walls defined here. There is one wall which is called wall no wet, and the other one is called wall wet. So if I display them here and I make them visible, so the one which is wall wet, you see that this is the wall that contains the ink, and the other one which is wall no wet is basically these two walls on the top. That means when the ink or the water coming on this surface, there is a good chance of wettability of these surfaces, while when it comes to this area, there is no chance of having this wall so much wetted as much as this one. So this is just a definition here in this problem, and you define it according to the boundary conditions here. So with the wall no wet, if you define the contact angle of 175, and what that means, I can show you contact angle wettability. If I can show you an image here, for example, here is a good picture that this displays and explains a little bit better the wettability and contact angle. So when the water touches a surface, and you see that the theta, the angle between the water droplets on the surface and the angles that it shapes with the wall is bigger than 90 degrees, that means that the water is hydrophobic. It doesn't like to, actually the surface is hydrophobic, so it doesn't like to have the water seated on its surface. If the theta is 90 degrees, it looks like this, and if it's if the theta is less than 90 degrees, as you see here, the surface is hydrophilic, which means that the surface likes the water, and the water touches the surface and actually spreads over the surface quite widely, as you see in the picture. So I'll come back to my geometry, to my Ansys Fluent here, and with the contact angles of 150-75 for the wall no wet, and 90 degrees for the other one, for the wall wet. You can repeat this simulation with different values and see the difference in the final results. This is actually an important parameters that shapes the droplet at the end and at the final results later. So the operating conditions, I will put the operating conditions of one bar at a location that you are sure that it's always air over there, and that is the x.1 and y like 0.03. So I think I'm done with the boundary conditions and the initial setups. Then I will go for the methods. In this simulation I would like to use this non-iterative time advancement, and I go for a scheme like fractional step, and for the momentum I pick quick, and for the volume fraction I will go for compressive. This non-iterative method is actually useful when you have when you don't want to when you don't want to have so much CPU consumption. So the method, the time advancement is non-iterative, and it takes less CPU, in fact. So if you want to understand these methodologies and these time advancement methods, I suggest you to consult the Ansys Fluent help itself. Then you may want to have some calculation activities, for example, and you may want to autosave your simulation, let's say every 2 time steps, and you may want to export your results as well, solution data export, in the format of CFT post compatible, and you may want to have I don't know, all this density, volume fraction, molecular viscosity for both air and ink, and then just press OK. And then it comes the initialization, and I will pick the standard initialization with the gauge pressure of 0 and velocities equal to 0 with the volume fraction to 0 as well, and I press initialize. But if you remember, at the initial time this chamber was filled with ink, so I need to mark this area and then come back to patching and fill this region with the ink. So what I need to do is actually I go to setting up the domain and mark adopt cells with the region, and specify the region that contains this ink chamber. So the x minimum and y minimum would be 0, but the x maximum would be 0.1 and y maximum would be 0.03. So if I just mark this region and you go to manage, you see that there is one region registered, and if you just display this, you can see that this region is now selected. So I will go to initialization again, and then patching, and then as you see here, this region that you registered is now available with the phase ink, with the volume fraction, and then you put the volume fraction to 1 and you just patch it. If you want to take a look at the patching, if it's done or not, you can go to contours, make a new one, and go for the volume fraction of let's say oil or the ink. Then just save display, and now you can see that this area that you patched it is filled with ink, and the rest is actually just air. So the initialization is also done, and then what you need to do is just to run a calculation. The time step should be very small because this is a problem that that everything is happening in microseconds. So I will put the time step to 1e minus 8, and then the number of time steps I would run for 3000, and you just press on calculate. Depending on your computer, this may take several hours, but I have done it actually I have done it I just want to show you how these iterations are being done, and I will stop it after a few iterations, and I will show you the final results. Okay, I will close this down. I have done this simulation before, and I just want to show you the videos that I have made in this for this simulation. So you see at time 0 the ink chamber is filled with ink and the rest is air. So I will let it go, and then it starts with a constant velocity of 3.58 at time 0, and then the velocity starts to decrease according to the cosine line defined for 10 milliseconds. So when it comes to 10 milliseconds, then the velocity, the injection, everything goes back to 0. But then you can see that this droplets are being formed in the air chamber, and it's still propagating in the air chamber. So one droplet is now elongated, and it's shaping 2 droplets. So you can see the surface tension working on the droplets. The second droplets is now immersed in the air chamber, and actually they are going downstream of the air chamber. So this was basically the tutorial I would like to show you. I hope you have learned something and enjoyed this tutorial as well. I will come back with more tutorials later. Thank you.